Okay, we record and second iteration. So it's my great pleasure to announce the first speaker in this afternoon session. It is Gerd Grubb from Copenhagen University, and she will tell us about non-local evolution equations. Please, Gerd.
Thank you, and thank you for organizing this wonderful meeting. I'm so happy that it's possible to celebrate Solonikov's birthday. I have known him since the late 70s when he came to Denmark, invited by me and together with a colleague, Hans True, at the Technical University. And I was working on pseudo-differential boundary value problems with a parameter, or a spectral parameter, or time derivative. And he was working on Navier-Stokes problems. And we were trying to see if we had something we could talk about. So Navier-Stokes problems are, as you will know well, degenerate parabolic systems of differential operators. So it's degenerate because there are second order and first order terms. It's an n+1 matrix. But what we found out was that this system could be reduced to a truly parabolic system by eliminating the divergence condition. So going out in full space, and the price one pays is that there's an extra term in the first line. Sorry, now something is covering my screen in the bottom. Anyway, I'll try to see what it says. Yeah, so we had a reduction where one eliminates the divergence condition, and then one has to put in an operator G here, a second order operator, which is non-local. So there's a non-local term G that had to be inserted, and then we get a parabolic case of the type I could treat. So we worked on that together. This operator G is a so-called singular green operator, and it belongs to a pseudo-differential boundary problem calculus that was initiated by Boutet de Montville. And we found a new solution method which gave good results, both in L2 settings and in LP for P between 1 and infinity. And that led to several papers, joint works, in Sapitsky 87 and 89, and in Journal Differential Equations, and in Matscant 91. And then I continued the work in papers up to 95. And we worked on smooth domains and smooth coefficients in the operators, but Helmut Abels later extended this to non-smooth X-dependence and non-smooth domains, beginning with a paper in 2005, and further contributions also together with other people. So we had a deal with non-local problems in those days. And now I will turn to my, one more remark. This calculus was for integer order operators, and the framework was originally introduced by Boutet de Montville. Now I'll turn to what I'm currently working on, namely, again, evolution problems, and again with non-local operators P, but the non-local thing about the current operators is that they are of fractional order, not necessarily integer order. So the evolution problem looks like this. There's the operator P and a time derivative and a boundary condition, which is here that U should be supported in the closure of the domain. And for initial condition, I just for simplicity take 0. And here P is, I can't see this part of the screen. So here, the prime example of P is the fractional Laplacian. The Laplacian lifted to the power A, where A lies between 0 and 1. And it can also be a more general pseudo-differential operator of order 2A. The Laplacian lifted to power A is of order 2A. So I'll tell you the story about this type of non-local operator. And here, I have to remind you what pseudo-differential operators are technically, because I think most of you don't use them every day. It's simply a very good application of Fourier transformation to treat operators that include differential operators and include their solution operators in many cases. So a pseudo-differential operator P with symbol little p of x and xi are variables in Rn. It's defined by use of the Fourier transform, where I stated here for my conventions. The Fourier transform is this formula. And the operator consists of, first you take the Fourier transform of u, that's a function of xi, and then you multiply it with px xi, and then you Fourier transform back this xi back to x. So x enters two places, both here and here. And that's the operator with symbol p. And when you don't have the x, I mean, when you don't just have a multiplication by a function of xi, then there is a very simple composition rule, namely, when you compose the operator with symbol a of xi with the operator with symbol b of xi, then that means you Fourier transform, multiply by b, take inverse Fourier transform again, multiply by a, and take inverse Fourier transform. And then these two cancel out, and you end up with the operator for which the function is a of xi times b of xi. Do you have remarks?
Давайте вечером.
What is wrong?
Вечером часов 9.
Excuse me.
Please proceed.
Okay, yes. Okay, so when we don't have this x dependence, it's a very simple rule, and that's really the explanation of the success of pseudo-differential operators that they compose so simply. If we do have x dependence, then just like for differential operators, you know, the Leibniz formula and so on, it's a little bit more complicated. Then the operator composed of two pseudo-differential operators has a symbol which is a product of the two symbols, and then a lower order term. So the function ax is called the symbol. And now let me turn to the operators I'm actually considering. I have a number a between 0 and 1. Px xi depends in a c tau, a Hölder tau way on x, and satisfies, and it is the infinity in xi, and satisfies such estimates. You also always need estimates of the symbols. The symbol itself is bounded by xi to the power 2a. This is sort of a smoothed out version of absolute xi. And the derivatives in xi are bounded by this power lowered by the order of the derivative. And then since we take c tau dependent on x, it's the c tau norm that has to satisfy this. So that's just the general class. And then I'm assuming three further things. P should be classical, means that it has an expansion in homogeneous terms, where the top term is homogeneous of degree 2a in xi. The next term is a homogeneous of degree 2a minus 1, and so on. And they should be strongly elliptic, which means that the principal term satisfies an estimate. Real part of the principal term is bounded below by a positive constant times xi to the power 2a. And then the third condition is special in what I'm talking about, namely P should be even. That's a shorthand for that it turns E, well, the long explanation is that it's even to even and odd to odd. That means that the terms with even numbers are symmetric in xi, and the terms with odd numbers are antisymmetric in xi. So these are the three basic hypotheses. And now I will tell you something about the operators. And before I get to the evolution problem, I have to look at the stationary case. So now I take such an operator, and you can think of the fractional Laplacian if you don't like to think of general pseudo-differential operators. And I take a domain, bounded open set with C1 plus tau boundary. And the problem with P is, one of the problems with it is that it's non-local. So it's only defined on Rn. Or if you look at its action on a function over a subset, then it's smeared out to the full Rn when you apply it. And the trick is then that we do restrictions anyway. So here is the homogeneous Dirichlet problem for P. It requires that we take functions U that are supported in the closure of omega, but so extended by 0 outside. And then we apply P to that, and then we look at what P is on omega, then it should match a given function F. So that's the Dirichlet problem. And here one could, for clarity, insert a restriction operator, R plus. R plus denotes restriction to omega. So it's R plus PU, that should equal F. And it turns out that it's not so hard to find a basic existence and uniqueness theorem by variational theory. So the idea is here that we give F in L2, and we look for U in HA supported in omega bar, and that the dot means supported in omega bar. And we use the sesquilinear form obtained by integrating PU times V over omega. Do it first for C0 infinity functions and then extend by continuity. Then we have a less sesquilinear form on the HA functions supported in omega bar. And it has a certain positivity, and that leads to Fredholm solvability. And now, when F is given in L2, we define the Dirichlet realization PD, which acts like R plus P, and has the domain consisting of those functions in HA supported in omega bar that hit L2 functions in this equation. So that is the Dirichlet realization, and then one can show that it is Fredholm in general, and it is bijective if you add a large enough constant. The hypotheses assure that. So we have a nice solvability in these very elementary spaces. But what's then a challenge, or was, before it was found out, is to find out where U really belongs when it lies in the domain. And you can also ask if the right-hand side F is in HS, where will U be in HS for some positive S? And now I'll get a little more technical. I have to introduce some function spaces. And now I take LQ theory into account. So S is a real number and Q lies between 1 and infinity. It's omitted when Q is 2. Then it's the ordinary Sobolev spaces. So here's the Sobolev-Slobodetsky space. It is, at least for S integer, it's the Sobolev-Slobodetsky space. Generally, it's called the Bessel potential space. It's the LP variant of the Sobolev space, where we require that when we multiply by psi to the S and Fourier transform back, we get something in LQ. This is the space over Rn, and along with it, there are two families of spaces over omega. The restricted space is simply the restrictions to omega of elements of HSQ. And we denote that with a line. And then there's the supported space. It's the functions that are in the space HSQ over Rn, but are supported in the closure of omega. And that's the one that has the dot. And this dotted line is not used by many people, at least the line is not used. The dot can be used. It's also sometimes it's a 0 or it's a twiddle, but this notation stems from Armando. Okay, omega is assumed to be open, bounded, and C1 plus tau, or it could be the half space. R plus denotes the restriction to omega, as I already said, and then E plus is the extension by zero operator. And I shall also need the trace operator, the boundary value here. And I shall also use, for a short remark, I shall use the Hölder-Zsigmondt scale. It's the Hölder spaces when S is a non-integer, positive non-integer, and that's filled out by the Hölder-Zsigmondt spaces in a nice way that are also defined for negative S. Okay, so what do we know about where U belongs? Wieschig and Eskin already had a theory going, and this is from the 60s and printed in Eskin's book from 81. They showed that the Dirichlet realization, the domain of the Dirichlet realization, is simply the dotted space for A less than a half. I mean, it's the H2A function supported in omega bar. And that's the best regularity you can ask for when F is in L2. And for A greater than a half, they could not show more than this. Namely, the domain is at least contained in HA plus a half minus an epsilon. Okay, that was an early result. And then recently, or more recently, there was another result by two young Spaniards. It was printed in 2014, namely, when F is a bounded function, then you can show that U has some Hölderness, that U is in a Hölder space with a small t times d to the a, where d is the distance from the boundary. And that's very important because they pointed out the importance of this factor d to the a. And then there's another result, a sort of that has not been noticed in the literature at all up until more recently, namely that Hermander had, he showed in a note, unpublished note, and he kept part of the details in one of his books, volume 3 of his big books, namely that F in C infinity holds if and only if U is in E in d to the a times C infinity up to the boundary. Is this black bar, is that visible to you also?
Oh, no, sorry, it's not visible. Can you try to enlarge to the full screen? Like, click
No,
this
I've already,
blue,
yeah, I've tried.
this blue box.
Yeah,
You have
yeah,
the blue
I think
box?
so. Wonderful. Now,
Oh, good. That's
now it
perfect.
works. Okay, good. So I go on. Yeah. So this was a very nice, complete result, which was not really noticed at all. I mean, deep inside this book, there is part of this result, mainly this implication from right to left, which is very important. Okay, and I got interested in the problem because of the result of Bossotton and Serre, because I was confused that so little was known. I couldn't understand that pseudo-differential operators hadn't been used. So it turned out I had this note in my possession. He had given it to me in 1980. And I looked at it, and then I could, there's another bar. And then I could complete it and show the following result, that F is in an HS space if and only if U is in a certain space here. And the importance is that it's an if and only if statement. And that held, that was valid in the smooth case for S going from a certain negative number up to infinity. And then some people have reproached me that this was all so smooth, only smooth sets, omega and so on. So I persuaded Helmut Abels to work with me on non-smooth cases, and we managed to do that in a publication that came out this year. Namely, we can go down to tau greater than 2a, so the symbol is c tau, and omega is c tau plus 1, and then S goes up from 0 to tau minus 2a. And exactly this bijectiveness holds, or this if and only if property holds. And as I've already tried to say, that these results are interesting because they're sharp. But what is this space? Well, it's a so-called A transmission space. And I will tell how it's defined in the half space case. Namely, it's a funny construction. It is, you take the restricted space with value A plus S, and then you apply this order reducing operator. It lifts the order by A, and you end up in a space which is not a nice, well-known space, but which has to be defined because it is the space that one reaches. But one can say a little bit more about it. It was introduced for Q equals 2 in Hamada's note and came out for general Q in my paper up here. It equals the dotted space in a small interval when A plus S lies between minus 1 over Q prime and 1 over Q. That's where this has nice bound. Does not, this is where this, it identifies with the dotted space. And then for higher S, it's the sum of the nice dotted space and an extra term that contains the distance to the boundary, d to the a, and multiplied with functions that are in the restricted space. And there's a little correction for some exceptional values. But this shows how d to the a comes into the picture. There's of course also a d to something here. The dotted space has a factor d to the 2a plus s times LQ. So the other thing that's remarkable is that these spaces are universal. They're independent of the exact symbol of P. So, I mean, they work for all P of the type I mentioned, but, and they show what the domain is up here. And to my knowledge, it's only the pseudo-differential methods that have given these precise results. There have been imprecise results, there have been inclusions known by other methods. Okay, in particular, the Dirichlet domain, which is the one where P hits L2, that's then this transmission space HA of 2A, according to the definition up here. And as I said, for A less than a half, it's simply the dotted space, and for A greater than a half, it satisfies this type of property. And here one can also be more precise. When A is greater than a half, then the d to the a part, this extra part, besides the dotted part, is d to the a times a certain Poisson operator applied to boundary values. Okay, so that is a precise description. And I won't say any much about the proofs, but I would say the fractional problems do not belong to this Boutet-de-Monvel calculus that I discussed with Shaver many years ago. But it turns out that one of the tools in how you prove these things is to reduce the question to a situation in the Boutet-de-Monvel calculus. You compose this operator with these order reducing operators on the right and left to a situation where you can use the techniques from the Boutet-de-Monvel calculus, which he initiated in 1971, and where I've written lots of stuff about it and developed it more. And then these A transmission spaces come out as a byproduct of that reduction. I should mention just in passing that one can also introduce a non-homogeneous boundary condition, namely that the boundary value not of u, but of u divided by distance to the power a minus 1 should match a function psi on the boundary, which has good solvability properties in the a minus 1 transmission spaces. And now I have presented some things rapidly to you, and then I will go on to the evolution problem. So now consider the evolution problem of the heat equation, where we have the p here and we have a time derivative and it should match a function given on the right-hand side. The boundary condition is that the function vanishes outside omega. One could also take a non-homogeneous boundary condition, but I won't have time to tell about that. So here's the problem. And of course, one will attack it with all the methods one can think of. And functional analysis will, of course, be a nice thing to use. So if we know things about P of the Dirichlet realization, and yeah, PD was the L2 Dirichlet realization, and we can take analogous realizations in LQ. And then from that knowledge, one can apply functional analysis methods and semigroup theory and try to get basic existence results. So for Q equals 2, it's easy. One can go back to Lyon's and Magenis methods from the book of 68 in French. It came later in English. And so one gets the following theorem. I pointed it out in the smooth case in papers in 2018, and in the non-smooth cases, I have a very recent publication in Journal of Functional Analysis based on the work with Helmut Abels. And the result is, for any right-hand side, for any f in L2 of omega times I, the t interval, there is a unique solution depending continuously on t with values in 2, and it satisfies that it is L2 with values in the domain of the Dirichlet realization, and it's H1 in T with values in L2. And I recall that the Dirichlet domain is this transmission space. Okay, so that's a basic result that comes out just from knowing positivity and estimates, simple estimates. But then there's a nice theorem in Lyon's and Magenis book that can be used to lift it a little bit. You could ask for, what about more regularity in X? What about more regularity in T? And it's possible to lift the regularity a little bit in X and it's a lot in T. And the main statement is, take an R between 0 and 2A, which is less than A plus a half, and give F in L2 valued in HR. So we lift the L2 to the HR, and we also lift the T properties to say that it should be differentiable, Sobolev differentiable up to order K in T. And then we can show that U correspondingly is L2 of I into the appropriate transmission space, the one that matches this right-hand side, and it lifts the T regularity by 1. So that's an okay result, but note that it only works for low values of R. And I don't think that's an accident. I think it's part of the fate of such problems, the non-locality. Well, I have other evidence for that I won't have time to tell about. Now comes the question, oh yeah, I should mention there are other works. There is some names, Felsinger and Kastman and Chanlar and Davila did work on Hölder properties, Jin and Xong on Schauder estimates, Lenore, Paral, Primo, and Soria on LR to LQ estimates, all for the fractional Laplacian. And then also Tong has something more with Fernandez Real and with Vivas. They did some results on anisotropic Hölder estimates, which are really good, for P equal to the fractional Laplacian and some X-independent generalizations. And now I get to the question of LP. So for LP, the results are more scarce. And for me, I had to turn to probability results, namely the results from probability which apply to the operators that are symmetric and X-independent. Well, I'll be more precise in a moment. And here the realization is what's called submarkovian. And I have to put an extra hypothesis, and the hypothesis is the symbol P of xi is x independent. It's real and positive, of course, and it's homogeneous for xi different from 0. That means there's only a principal part for the result I'm not going to state. So here comes the theorem. Assume, in addition to the previous assumptions, also this assumption 4. Then, when Q is between 1 and infinity, the evolution problem has for any f in LQ of omega times I a unique solution continuous on I valued in LQ, which satisfies U is in LQ of I valued in the domain space for the Dirichlet realization, intersected with H1 in Q valued in LQ. And this is optimal. This is what is called maximal LQ regularity. So one can get that in this under this extra hypothesis. And the proof uses the sesquilinear form I had on the board for real U and V, and uses that it's a so-called Dirichlet form, as described in books of Brian Davis and by Fukushima, Oshima, and Takeda. And then one can apply a nice result of Lamberton, which showed that then one has this solvability for the evolution problem. And then this theorem implies also a resolvent estimate that I am stating here. Make these assumptions, then there exist constants such that the resolvent, the LQ norm of the resolvent is bounded below by positive constant times lambda times U LQ norm. This is the important term. And also U, the norm in the Dirichlet realization space. That comes automatically, actually. And that holds in a certain sector that I will now define. It's a sectorial region. It's the complement of a convex sector to the right. So it's a region where the argument goes from p half minus delta in the complex plane down to 3p half plus delta. So it's a left sectorial region, and let's cut out something around 0. So there is a nice resolvent estimate, and such resolvent estimates are also very useful, and they allow to show estimates with high regularity in T, at least by methods of Amann from 97 and other people, namely the following. Here is an example of what we can get. Make these assumptions, and then the solution satisfies that when F is given Hölder continuous, and for simplicity, take the full T interval from 0 to infinity, the dot means it's 0 below T equals 0. Take an F in this space valued in LQ, then U will lie in the same space valued in the Dirichlet domain, and the space lifted by 1 in T valued in LQ, and that is also an if and only if statement. And this dotted space denotes a set of U in CS that vanish for T less than 0. And here it's, I mean, I can omit the star when S is non-integer. So there's a statement here. And unfortunately, it's not what is called maximal LQ regularity, because that requires an LQ in front. But it's certainly interesting too. So this is where the theory stands, but I will now go on to telling a little bit of what I'm currently struggling with, what I'm trying to do for the moment. So let me tell a little about work in progress. So my current work deals with the question of what can be obtained without this Markovian property. So I'm taking X-dependent operators that are not necessarily symmetric. And my first attempt was to go back to the old discussion I had with Solonikov, namely for the linearized Navier-Stokes problem, we had the strategies that we could use it to, we could reduce it to a pseudo-differential problem in the Boutet-de-Monvel calculus. And the general type is like this. There's a P pseudo-differential operator, a G singular green term, there's a trace operator, and then an initial condition. And I tried, could I do the same here? So what we did together was that we treated this by parameter-dependent versions of the calculus. I mean, where you build in a parameter in the symbol, either the spectral parameter or a time parameter. And we could get through on that. And we got both maximal LQ regularity and all the higher order estimates you'd like. And it came out in a joint work with Solonikov handling the case Q equals 2, and in another work I did later where I gave the full story for general Q. And then the idea was, or my idea now was, can I do something like this for the new problems? But unfortunately, it's not really successful at the boundary. At least what I've tried to do is not successful. I could say there are good results for the full space where estimates over the full space are fine. It can be done with a parameter-dependent variant. And for interior estimates, local estimates inside omega, it's also good. But boundary estimates were not good. There's a very small window where they work, namely if A is less than a half and Q lies between 2 and the inverse of A. Here one gets the nice result, but that's not interesting enough. So for the moment, this has been abandoned, this method. Another method, another natural thing to do would be to apply perturbation methods to try to extend the result of theorem 2 or the resolvent estimates afterwards from the X-independent real case to more general symbols. And here there are some perturbation methods in the joint work with Abels, which also allow non-smoothness. And what they can do is the following. So here's a theorem. So now I go back to the general case, bounded, omega is bounded with C1 plus tau boundary. P is an operator that satisfies only the first 3 hypotheses and with an X-dependent symbol, depending C tau on X. Then I have an extra assumption that I would have hoped to live without, but the assumption is that the principal symbol is real positive at each boundary point. So it is a small restriction, but at least something comes out of this effort. And it's the following. Then there are constants such that that P minus lambda satisfies the resolvent estimates I had on the previous board. It's the same thing. P minus lambda U is bounded below by a positive constant times lambda U LQ norm, and then plus this term, which belongs naturally there for some sectorial region. So that could be shown, and that leads to an evolution equation result, namely that under these hypotheses we can use the techniques of Amann and others to show that there is a solution when F is in some Hölder class in T, valued in LQ. It gives a solution U in the same Hölder class valued in the domain of the Dirichlet realization, intersected with one better Hölder class in T, valued in LQ. And that's not quite the maximal LQ regularity, which seems to require some further techniques. So that was what I wanted to show. And I have a list of references that I will just pass through without expecting you to read it, but you can get the slides from me if you want. And then I will end up by saying, dear Sheva, congratulations with your 90 years.
Okay, thank you, Gerd. You are perfect in time, and thank you for the wonderful talk. What about questions?
And I get back to seeing you. I would like.
Yes. Okay, Maurizio, please ask your question. Maurizio Grazielli.
No, sorry about that. My mistake. So sorry.
It's mistake, okay?
Yes, just a mistake.
Yeah, I cannot see your faces, so I'm sorry.
Okay.
Okay.
Jose Francisco?
Oh,
Just-
yes. I really enjoy very much your talk. I'm wondering, when you spoke about evolution problems, basically what you did is for, say, a parabolic type. I'm wondering if you can, I mean, type equations. Can you also handle wave type equations, evolution of second order in time?
I must admit I have not tried. I mean, hyperbolic questions are a little different. I mean, elliptic and parabolic are very much in the same basket, and hyperbolic usually requires something quite different. And I have not tried. I mean, somebody should try. And of course, if this sort of right away functional analysis results that you can do for the wave equation, you can certainly do them here too, in L2, but I don't know anything about LP results. So I would say it's up to somebody else to try.
Okay, but at least L2, it should work directly.
Something should work, certainly, yes,
Okay.
yes.
Thank you. Thank you.
Okay, next question, Helmut.
Yeah, first of all, thank you for the nice talk, Gerd. So I have a comment and maybe a question. Yeah, one comment concerning this estimate 7 you had, which was you had this maximal AP regularity in the constant coefficient case using the Markovian properties or sub-Markovian properties, and then you derived this this resolvent estimate. One comment is, yes, exactly that. Is that, of course, here you would get immediately in 7 also that the estimates are R-bounded.
Well, if you do that, that gives me hopes. Yes.
Yeah,
no.
since that's there's a general theorem that a maximum regularity of an operator is equivalent to R-bounded resolvent estimate.
Sure. That would be.
And then maybe this can improve some of these things.
Look, yeah, if this one implies R-boundedness, then I'm done. Yeah, that would be wonderful. Well, I would be done in the non-smooth case, at least under that special assumption at the boundary. Yeah.
Mm-hmm.
But I thought this estimate was a corollary to the Markovian property, or to the yeah. Let me get back to the previous slide.
But if you have the slide before.
Yeah. I thought. I mean that the estimate 7. I see that it as a corollary of this information, but I didn't think it was equivalent. But if you this.
Yeah, but this is for instance in the monograph by Denk-Hieber Prüß.
Okay.
There's a theorem on really maximal AP regularity for an general operator. Of course, you need some technical assumption like UMD space, but you have that is equivalent to R-bounded resolvent estimate.
That would be wonderful. Yeah, it would. That would give a big step forward. Yeah. If I could appeal to that. I've been looking into those books and I have not been able to find this, but maybe we can discuss it more. Yeah,
sure.
Yeah.
Okay, more questions? If it's not the case, let's thank the speaker again.
Thank you.
Okay, Gerd, please stop share your screen, and Sasha, please give the rights for Grigor Alexandrovich.
Moment.
How do we do that? I'll stop share. How do we stop share? Oh, now I'll go back to share and try to find the correct button. There should be a button down here. Well, I'll try Control L.
Okay, that's okay.
Now, good. Yes.
Okay, Sasha, you can. Grigor Alexandrovich, вы имеете право co-hosta. You have a co-host right now, and please share your screen.